Hello, I am Valentina De Chan and I am a software engineer at DNA Algo. This video is an introduction to the topic of error correction codes in DNA storage. We have already seen what an error correction code is, and as an example, we have talked about the Hamming 7.4 code. This code belongs to the family of block codes. A block code is an error correction code that takes an input of fixed size k, adds some redundancy, and produces a code word of length n. The ratio k over n is called code rate. Block codes are very interesting from the mathematical point of view, especially because we can represent encoding and decoding through matrix multiplication. We can take, again, the Hamming 7.4 code as an example. The encoding procedure can be performed through this matrix multiplication. We have to take the input data and multiply it by a special matrix called generator matrix. This matrix depends on the specific code we are using. For example, this is the generator matrix of the Hamming 7.4 code. The result of this matrix multiplication is called the code word and is the encoded version of the input data. This is a simple row-by-column multiplication model 2, which means that, for example, the first bit of the code word can be computed through these calculations, that are the multiplication of the input data by the first column of the generator matrix, 0 by 1 plus 1 by 0 plus 1 by 0 plus 0 by 0 module 2, which gives 0. In the same way, through the multiplication of the input data and the second column of the generator matrix, we get the second bit of the code word, and so on. We can check that the result is actually the same that we have computed using the parity equations of the Hamming code. So the result is the same. This is just a more general way to describe the encoding procedure for block codes. Well, this in the yellow box is a fundamental rule for matrix multiplication. It says that we can multiply matrix A by matrix B if and only if the number of columns of A is equal to the number of rows of B. And we can see it in our example because the number of columns of the first matrix is 4, and 4 is also the number of rows of the second matrix. So this multiplication is allowed and we can compute the code word. This is a fundamental rule and we will need it later. Now that we have seen the encoding, we can pass to decoding. This time we need another matrix called parity check matrix that also depends on the specific code we are using. This is the parity check matrix for the Hamming 7.4 code. We have to multiply this matrix by the code word received from the channel. You can see that the code word is written as a column vector because in this way the dimensions of these two matrices match and the rule that we have just seen is respected, so we can perform this multiplication. The result of such multiplication is called syndrome. Well, the syndrome is not the decoded code word, but it gives us information about the errors in the code word. For example, in this first case, the syndrome is the all zero vector, and this means that the code word has no errors. While in this second case, the syndrome is not the all zero vector, which means that there are errors in the code word. So when we compute the syndrome, error detection is always guaranteed, but error correction is not. This depends on the specific code we are using and also on the number of bits in error. In this particular example, we can also correct the bit in error. In this way, we have to look at the column of the parity check matrix that is equal to the syndrome, 1, 0, 1. The index of the column in the matrix, which is 4, gives us the position of the bit in error, which is the fourth. So in this particular case, we can also correct errors, but it is not always the case. Now, let's try to put our Hamming 7.4 code into a basic DNA storage system. Suppose that we have some input data and we want to store this information in the strand of synthetic DNA. First, we have to encode our data using the encoder of the Hamming 7.4 code. This is the code word. Then we map bits to nucleotides, and we get, for example, this DNA strand. We can synthesize this strand, and after a while, we want to recover the information in it. So, through DNA sequencing, we get, for example, this DNA strand. The DNA channel can be modeled as an IDS channel. So we can suppose to have, for example, a substitution. Here we have C instead of G, and also an insertion because there is a new T. To this DNA strand, we apply reverse mapping to get a sequence of bits, and then we have the last step, that is the ECC decoding. We would like to decode such a sequence of bits to recover our initial data. The decoder would like to compute the syndrome of this sequence of bits, and so it has to multiply the parity check matrix of the Hamming 7.4 code by the transpose of this sequence. But the problem here is that the number of columns of the parity check matrix is 7, while the length of this sequence is 9. So these two dimensions do not match, and the rule for matrix multiplication is not respected. The decoder gets stuck. It cannot compute the syndrome, it cannot decode the sequence of bits. So it has to discard the sequence and lose the information that it was trying to recover. To sum up, the problem with IDS channel and block codes is the fact that this particular channel can change the length of the strands, and this is a very big problem for block codes, because if the input of the decoder is of unexpected length, the decoder can only claim that there are errors, but it is not able to correct them. So detection is still present, but there is no possibility of correction. We have to discard the strand and lose the information we were trying to recover. In conclusion, block codes are a very powerful tool. But in order to put them into a DNA storage context, the basic scheme that we have seen in the previous slide is not enough to achieve an acceptable performance. For example, we could try to modify it a bit, adding some steps like clustering and trace reconstruction that we have already seen in order to try to mitigate this problem. Or also we can think of using codes that are more suited to the IDS channel, such as fountain codes, for example. That's it. If you would like to know more about this topic, subscribe to our website dnaalgo.com. Thank you very much. Hope you enjoyed it.